Hey everyone, ready for another deep dive? Today we're tackling chemistry, specifically the stuff from your ninth grade textbook.
Yeah, that's right. We're going back to school.
Oh, ninth grade, that brings back memories.
It does, doesn't it?
Huh.
Well, get ready because today we're uncovering the truth about what's actually pure and what just looks that way.
Hmm, I'm intrigued.
Think about it. We see things like salt milk, even the air we breathe, and think, yep, those seem pretty pure.
Right, totally.
But guess what? Scientists would actually say those aren't pure substances at all.
Oh, really? Okay, I'm listening.
Yeah, so that's what we're getting into today. The difference between what we think of as pure and what's really pure, according to science.
This is gonna be good.
I know, right? And we've got some awesome visuals from your textbook to help us along the way.
Hmm.
So let's jump right in.
Okay, so our textbook shows these pictures of salt milk, all these things that look pretty pure, right?
Yeah, I mean, at first glance, I'd say so.
Exactly. But here's the twist. They're actually mixtures, not pure substances at all.
Interesting. So what makes something scientifically pure then?
Well, that's where the science comes in. So a pure substance in science means it's made up of only one type of particle, and it has the same chemical composition all the way through.
Okay, so a pure substance is like completely uniform all the way down to the tiniest particles.
You got it. So imagine something like distilled water.
Hmm.
It's just water molecules and nothing else.
Mm.
That's pure.
Ah, okay, I see.
But then you think about tap water, even if it looks crystal clear, it still has other minerals and stuff dissolved in it.
Yeah, that makes sense. It's like even when my classroom looks empty, there's still dust particles floating around.
Exactly. It's all about what you can't see. So tap water, even though it looks pure, it's actually a mixture.
So even if something looks pure, it might not be scientifically pure. I get it.
Right. And that's where things get interesting. So, okay, we've talked about pure, but what about mixtures? What are those all about?
Well, a good way to think about it is like combining ingredients in a recipe.
Okay. I like where this is going.
Each ingredient keeps its own identity, right? Even when they're all mixed up together.
Yeah, like flour and sugar in a cake batter. They're all mixed up, but you can still kind of picture the individual grains.
Exactly. So that's the basic idea of a mixture. It's a combination of two or more pure substances, but each substance keeps its own properties.
Gotcha. So it's not like they melt into one new thing. They just hang out together.
Right. Now, mixtures can be categorized based on how evenly those substances are spread out.
So some mixtures are more well-mixed than others.
Exactly. We call those homogeneous and heterogeneous mixtures.
Okay, two new words for us. Break it down for me.
Okay, so imagine dissolving sugar in water. You get a homogeneous mixture because the sugar molecules spread out evenly.
Like every sip is equally sweet.
Exactly. Every part of that mixture is the same. Now, our textbook mentions an experiment with copper sulfate.
Oh, yeah, I remember that one. What was that all about?
It's a great example of how even within a homogeneous mixture, the concentration can vary.
Concentration.
Yeah.
Like how strong something is.
You got it. In that experiment, you can make the solution darker blue by adding more copper sulfate, but it's still homogeneous.
Oh, so the color tells you how much is dissolved.
That's cool.
Right. It's a visual way to understand concentration. Now, heterogeneous mixtures are a bit different.
Okay, how so?
In a heterogeneous mixture, the components stay separate. Think of a salad.
You can see the lettuce, the tomatoes, all the separate parts.
Exactly. Or sand and iron filings mixed together. You can easily tell them apart.
Or oil and water. They just never really mix, right?
Exactly. So those are the two main types of mixtures. But it gets even more interesting when we look closer at the size of the particles.
Okay, now I'm really curious. Particle size. What does that have to do with anything?
Well, that's how we get solutions, suspensions, and colloids. And they all have very different properties.
All right, I'm ready. Lay it on me. What makes a mixture a solution? A suspension or a colloid?
Let's start with solutions. They have the tiniest particles so small you can't even see them with a regular microscope.
Wow, that's tiny.
Right. And because they're so small, they don't settle over time, and light can pass right through them.
Think about salt water. It's a solution. Or even the air we breathe. That's a solution too.
Whoa. I never thought of air as a solution.
It is. So you see, solutions are all around us. Now, suspensions are different.
Okay, I'm listening.
They have much larger particles that you can see. Think about muddy water. If you let it sit, what happens?
The mud sinks to the bottom.
Exactly. That's because the particles are big enough for gravity to pull them down.
Makes sense.
And remember that filtration experiment from the textbook?
Yeah, vaguely.
That's a perfect way to separate the parts of a suspension.
So solutions have teeny tiny particles that don't settle, And suspensions have big, visible particles that do settle.
You got it. Now, where do you think colloids fit in?
Hmm. Well, if solutions are tiny and suspensions are big, colloids must be somewhere in between.
You are absolutely right. Colloids are the in-betweeners. Their particles are bigger than solution particles, but smaller than suspension particles.
Interesting. So what does that mean for how they behave?
Well, it gives them some unique properties, like the way they scatter light. It's called the Tyndall effect.
The Tyndall effect. Okay, that sounds fancy.
It's actually pretty simple. Have you ever seen how car headlights look in fog?
Yeah, they make like a beam of light.
Exactly. That's the Tyndall effect in action. The fog, which is a colloid, scatters the light from the headlights.
Oh, I get it. So it's all about how those particles interact with the light.
Precisely. Now remember that picture in your textbook of sunlight shining through a forest?
Yeah, with the beams of light coming through the trees.
That's another example of the Tyndall effect.
Mm.
The mist in the forest acts as a colloid scattering the light.
Cool. And milk is a colloid too, right?
Yes. Milk is a colloid because the tiny fat droplets are spread throughout the water, and they scatter light, giving milk that cloudy look.
That's fascinating. So we've covered pure substances, and now all these different types of mixtures, solutions, suspensions, colloids. It feels like we're really starting to break down the stuff that makes up our world.
We are, and it's all thanks to chemistry.
This is awesome. So where do we go from here? What's next in our chemistry adventure?
Well, now that we've got a good handle on mixtures, I think it's time to zoom in on solutions, since they're so important and everywhere.
Okay, I'm ready. Let's dive deeper into the world of solutions.
Okay, so solutions are everywhere, right? But what exactly makes them tick?
Yeah, I'm ready to get into the nitty-gritty of solutions, what makes them work.
Well, let's break down the key players. We've got the solute, that's the substance that dissolves,
Oh,
and then we've got the solvent, that's the substance that does the dissolving. Think about making hot chocolate.
Now you're talking about language.
Right, so you've got your chocolate powder, that's the solute,
Okay.
and you stir it into your hot milk, which is the solvent.
Ah, so the milk is doing the dissolving work.
Exactly, and you usually have way more milk than chocolate powder, right?
Yeah, that's how you get a good chocolate to milk ratio.
Precisely. So the solvent is usually the larger part of the solution.
Makes sense.
Okay.
So in salt water, then the salt is the solute and the water is the solvent.
Bingo. You got it. Now, once the solute dissolves, it spreads out evenly throughout the solvent. That's why every sip of your hot chocolate tastes the same.
Yeah, otherwise you'd get one super chocolatey sip and then a blah one.
Exactly. And that brings us to another key concept, concentration.
Concentration.
Mm-hmm.
Okay, I think I remember that from the textbook.
It tells us how much solute is dissolved in a certain amount of solvent.
So like a really strong cup of coffee would have a higher concentration of coffee grounds.
You got it. More bang for your buck, right? The textbook mentions different ways to express this, like percentages, but the main idea is that concentration tells us how strong the solution is, how much solute is packed in there.
Right, so it's all about the ratio of solute to solvent.
Mm.
Okay, that makes sense. What about saturation, though? The textbook mentioned that, too.
Ah, saturation. That's where things get interesting. Imagine you're making iced tea and you keep adding sugar.
Okay.
At first it dissolves, no problem. But if you keep adding more and more sugar, eventually it won't dissolve anymore.
Yeah, it just sits at the bottom of the glass.
Exactly. That's because the tea has reached its saturation point. It's like it's full of sugar. It can't hold anymore.
Like a sponge that can only soak up so much water.
Perfect analogy. And just like a sponge can hold more water when it's warm, a substance's solubility, how much solute it can hold, also changes with temperature.
Oh, right. That's probably why recipes always tell you to heat the water before dissolving stuff.
Exactly. Heating things up gives those solvent molecules more energy to break apart the solute and make a more concentrated solution.
So it's like giving them a boost to do their dissolving work.
You got it.
This is all making so much sense. We started with pure substances, then mixtures, and now we're really getting into the details of solutions. It's like we're building this whole chemistry toolbox.
We are. And with each new concept we add to that toolbox, we can understand the world around us even better.
It's awesome. So what's next? What other tools are we adding to our chemistry belt today?
Well, now that we've explored mixtures and zoomed in on solutions, I think it's time to go back to the basics. The building blocks of everything. Elements and compounds.
Back to the basics. Okay, I'm ready. Tell me about elements and compounds. What are those all about?
All right, so we've talked about elements and compounds, the building blocks, and how they can react and form new substances, right?
Right. It's like building something totally new from smaller pieces.
Exactly. So now let's look at how matter changes, both physically and chemically.
Okay, so we're talking transformations now.
Yeah.
How things can change I'm ready.
Great. Let's start with physical changes. These are changes where the substance itself stays the same, even if its shape or appearance changes. Think about cutting a piece of paper.
Okay.
It's still paper, right? Just a different shape.
Yeah, it's just smaller pieces of paper.
Exactly. Or think about ice melting into water.
It's still water, just in a different form.
You got it. The chemical identity of the substance stays the same, but with a chemical change, you're actually creating something new, something with a different chemical composition altogether. Think about bringing wood.
Okay, so you start with wood and end up with ash and smoke. Totally different.
Right. The wood reacts with oxygen in the air and produces all these new substances like carbon dioxide, water vapor, ash.
So burning wood is definitely a chemical change. You're making something totally new.
Exactly. The key is that the original substance is transformed into something new with new properties.
Oh, I see. So it's not just about changing shape, it's about creating something completely different.
Right. Now, the textbook mentioned dissolving salt in water as a physical change.
Yeah, but doesn't the salt disappear when you dissolve it?
It seems that way, right? But the salt is actually still there. It's just broken down into tiny particles that are spread out in the water. You can get the salt back if you evaporate the water.
Oh, so it's not gone, it's just hiding.
Exactly.
Uh-huh.
And because no new substance is formed, it's a physical change, not a chemical change, just a rearrangement of the salt particles.
Gotcha. So it's still salt, it hasn't transformed into something else.
Precisely.
This is really cool. We've gone from pure substances to mixtures to solutions to elements and compounds. And now we can even tell the difference between physical and chemical changes.
I know it's a lot, but you're doing great.
I'm feeling like a real chemist now.
You should. We've covered so much ground today. It's like we've unlocked a whole new way of seeing the world.
It really is. Okay, so let's do a quick recap of everything we've learned in this chemistry deep dive.
Sounds good. We started by busting some myths about what pure really means in science. Remember, a pure substance is made of only one type of particle.
Yeah, like distilled water or pure gold.
Right. Then we dove into the world of mixtures, where different substances mingle and create all sorts of interesting combinations.
We learned about homogeneous mixtures, where everything's evenly spread out, and heterogeneous mixtures, where you can still see the different parts.
And who could forget about solutions, suspensions, and colloids?
Those were fun. Solutions with their tiny dissolved particles, suspensions with their larger particles that settle, and colloids, the in-betweeners that scatter light and make cool effects.
We even got to play chemist and make some solutions ourselves.
Yeah, that was cool. And we learned about solutes, the things that dissolve, and solvents, the things that do the dissolving.
Plus, we tackled concentration, how much solute is packed into a solution, and saturation, the point where a solution just can't hold any more solute.
Right. It's like a sponge that's full of water.
Perfect analogy. Then we went back to basics and explored elements, the fundamental building blocks of matter and compounds formed when elements combine in specific ways.
And finally, we learned to tell the difference between physical changes, where a substance keeps its identity, but maybe changes its form, and chemical changes, where a new substance is created altogether.
We've really covered a lot of ground, haven't we?
We have. And the coolest thing is that this is just the beginning of our chemistry journey. There's so much more to explore.
Absolutely. So here's a final thought for all our listeners. Take a look around you right now. Can you spot any examples of the things we talked about today?
Yeah. Can you find any pure substances, mixtures, elements, compounds? What about physical or chemical changes happening right before your eyes?
Remember, chemistry is happening all around us all the time.
It really is. Keep those brains buzzing, future chemists. Until next time, stay curious.